the growth of trees in a forest, you cannot just discuss it in terms of an isolated tree. The tree belongs to a forest, and the height to which it grows, is determined by everything in the forest, and believe it or not, includes everything from bacteria in the soil to animals, birds, snakes, insects, and so on. And you may ask, what about Darwin's law and all that? Well, Darwin's law of the fittest operates among species on a very large time scale, often hundreds of thousands of years, before one species wins over all the rest. But if you take a shorter time scale, say 10,000 years or so, the forest grows in such a manner that there is harmony in the overall growth. The lion may eat the deer, but nature maintains an overall balance, allowing for everyone to take, but they must also give. In other words, there is generally no free lunch. I stress this point because these days, the economics seems to be the winner takes all. Even recently, just as recently as last Sunday before last, I heard the head of Goldman Sachs appearing in an interview with Fareed Zakaria. And Fareed Zakaria was talking about economic inequity in America. And Goldman Sachs chief smiles and says, well, Fareed, in this day, you know, the winner believes he's entitled to take all. Some people suffer, we have to worry about them and all that. That is crocodile shedding tears, and I think crocodile will lose in this case. Now, to get back to the forest, it is an entire ecosystem, and every single entity has to exist in harmony with the entire ecosystem. Stated differently, growth of every constituent element in an ecosystem has to be consistent with the sustainability of the system as a whole. And incidentally, nature has taken care of this in forests by hardwiring all the species that exist in the rainforests. But if you take the planet Earth as a whole, we occupy a whole lot of the land mass. And nature has not hardwired us. Nature has given us a brain and a buddhi. And we are supposed to be in harmony with the rest of the ecosystem. And we are not, and that's where all the problems come. And if we were in harmony, there would be no need for me to come here and give this lecture. So now, let me talk about order in nature. So far, I have been talking about this tussle between growth and sustainability, and I would like to talk about order. Now, the word order is used in physics in a number of ways, all the way from the micro to the macro. And of these types of order, I will consider only macro order, and only two examples, positional order and magnetic order. And it turns out I can discuss both conveniently with the help of one example. But before that, I want you to understand what do I mean by positional order. So let me look at the next slide. This is supposed to be the cross-section of the sun. I have taken the sun to show a physical system where there is no positional order. Now, if you take the sun is a star, and there are many kinds of stars. The simplest star, which probably that was the kind that existed something like 100,000 years after the universe was born, which was about 13.8 billion years ago. In the beginning, there were no stars, but the first stars formed about 100,000 years after the universe was born. And they were born when there was enough hydrogen in the gas cloud for it to shrink and make it hot. In those stars, they were helium-burning stars. The hydrogen atom consists of a proton and electron, but because of the high temperature, they break apart. And all these protons are moving wildly, and the electrons even more wildly. So you have absolute randomness. And that is because of the very great heat, which is caused by hydrogen burning. When I say burning, it's not like burning in a flame. It's nuclear burning where hydrogen comes together to form helium. It's a very complex process, but the heat released is 10,000 times what you get in a chemical reaction. Thus, the temperature of the sun would be 1,000,000 degrees very easily. And at that time, matter tears apart and there is disorder. So the points to note are the temperature is very high and there is no positional order. The take-home lesson is that at high temperatures, the particles move about at such high speeds that positional order is impossible. Let us now look at the next 3 slides. First, I go to the next slide. This shows a slide of quartz. The beautiful thing is it has got faces. Long ago, long before the atoms were physically discovered with electron microscopy and all that, the scientists in the 19th century figured out that the atoms must be arranged in lattices. Otherwise, you won't get these faces. By the way, this is a naturally found quartz, but you can now grow quartz in the laboratory also. And people collect these kind of quartz found in nature. And let us see the next slide. Here you have a crystal of silicon. Now this doesn't have faces because this was grown in a machine. And this fellow is handling this. You may say, well, why does he spend his time growing a silicon crystal? The next slide will give you a clue to it. This shows a slice of a silicon crystal. This will be roughly 20 centimeters across. The slice will be very thick, 1 millimeter or so. And this is very valuable because out of this slice of silicon, you can get about 100 chips. And those are the chips that power your iPad, which Sachidit is using, or the cell phones which you all have in your pockets, and your TV sets and so on. So this silicon is just mud. Huh? Mud is silicate. From that, by refining, man has produced silicon crystals, and he is making use of them in many ways. Now, I was talking about positional order, so let us look at the structure of silicon. The next slide, please. This is a schematic. This is supposed to show silicon atoms. There are atoms at the edge of this cube, and there are atoms inside also. This structure is called by a certain name, and I will explain what that name is very shortly. But before that, let us suppose I replace every one of these silicon atoms by carbon. Suddenly you will get something very valuable. And why? Because when the silicon structure is given to carbon, it becomes diamond. Therefore, this structure is called diamond structure. Germanium, silicon, and carbon all have this structure. But then, when the carbon has it, it becomes very valuable. By the way, carbon has another structure that is called graphite. And we all know graphite. So it can become very inexpensive or it can become very expensive depending on its mood. And incidentally, in nature they have found a star which is huge and it is completely diamond. And it's called Lucy because I'm told there's a poem called, about Lucy and diamond. We used to sing, "Twinkle, twinkle, little star, how like a diamond." How does it go? I forgot. I went to kindergarten about 75 years ago, so I am entitled to forget it. But there is a star. It's called Lucy. It's a white dwarf, and it's all diamonds. So anybody wants to go rich, go take a ride there. Now the take-home lesson is the entire silicon is obtained by just repeating this again and again. Now, what do we learn from this in the sun? If you lower the temperature, you get order. Keep that in mind. I would now like to discuss iron, because I have got 2 stories in one in the case of iron. We start with molten iron. And as we lower the temperature, it freezes. This happens in a factory with a blast furnace where they melt iron. The iron pours out and ultimately solidifies. That solidification takes place when the temperature comes down below 1,538 degrees Celsius. Today, the outside temperature is something like 22. 1,538 degrees centigrade is when iron freezes. At that time, you get positional order. And let us see what kind of positional order iron has. The next slide, please. Oh, by the way, this is what happens when you repeat the silicon. Again, a unit cell again and again. The whole of space is filled with this diamond structure. So next slide, please. This shows the unit cell of iron. There are iron atoms in the cube, and there is one at the center of the cube. And so this is called a body-centered cubic. cube has got atoms at the corner and one at the center also. If I repeat this extensively in all three directions, I get the structure of solid iron. And this happens when iron comes below 1538 degrees centigrade. The story does not stop here, because every atom of iron is like a tiny magnet that is connected with the internal electronic structure, and I won't go into that. Now, a magnet, as you know, has got a north pole and a south pole. The atomic magnet that iron is usually represented in the classroom by drawing an arrow, the arrowhead being the north pole and the bottom of the arrow being the south pole. So now the question is, as soon as you melt the iron and the iron freezes, there are all these magnets. Which way are they pointing? Are all the arrows pointing one way, or are they pointing in random directions? The answer is given in the next slide. Yes. So here are the arrows that represent the iron atoms. This is at 777 degrees centigrade. At this temperature, the atoms are in the lattice, but the arrows that they carry are pointing in different directions. So there is no magnetic order. But if you cool it below that, then the magnets it's like a parade, you know. When they say attention, everybody stands still. Till then, at ease means they sort of shuffle here and there. So this is at ease, atoms at ease. They are in a parade, but they are relaxed. And the commander says, shouts attention. This happens below a certain temperature called Curie temperature. So there is magnetic ordering. One interesting question can be asked, and that has got a fallout for a message for us, and that is given in the next slide. Supposing I take iron at this temperature, in the previous slide, hold it there. Supposing I keep it above the Curie temperature, that means it is a solid, but it is disordered. And now I bring a very strong magnetic field, then they are all in order. It's like, you know, a country with a dictatorship. People tend to be chaotic, but if emergency is imposed, bad word here, I know, then people become order. Everybody come to office at time, and so on and so forth. So very often we keep wishing for emergency. But the nature says, yes, I also have. But then there